Okay, so we're going to talk about bond energies and bond length. Individual bond energies can be used to estimate the enthalpy changes for a reaction. That was the delta H. And we define bond energy as the energy required to break 1 mole of that particular type of bond in the gas phase. Bond energies are always positive. It always requires energy to be put into the molecule to rip it apart. A bond is considered to be stronger if it takes more energy to break. Kind of makes sense. So we could look at hydrogen chloride in the gas state, and there's a bond between the hydrogen and the chlorine atom. And if we break that bond, we'd make a hydrogen atom and a chlorine atom, and that would require 431 kilojoules of energy. And the implication here is that it's kilojoules per mole. Okay? Kilojoules per mole. So a compound that has a stronger bonds, is held together by stronger bonds, tends to be more stable and less reactive than a compound with weaker bonds, because you have to break the existing bonds before you can form new ones. And so stronger bonds are harder to break. So bond energy varies a little bit. If we look at a carbon-hydrogen bond in different compounds, here we have a carbon-hydrogen bond where the carbon's bonded to 3 other hydrogens. That has a bond energy of 438. In this compound where the carbon's bonded to fluorine, the carbon-hydrogen bond is 446. It's stronger. Here with bromines, it's 402, and with chlorine, it's 401. So the same bond between carbon and hydrogen will vary in strength a little bit depending on what else is going on in the molecule. And so instead of trying to worry about exactly which thing we're dealing with, we usually talk about an average bond energy. So they've studied the bonds between carbon and hydrogen in lots of different compounds, and the average is 414 kilojoules. So that way we don't have to have ginormous tables of numbers. If you have a double bond, that's going to require more energy to break, and a triple bond will be even stronger. It'll have a higher bond energy. This is a table from Chapter 9 showing some average bond energies. There's a more extensive table in the appendix in the back of the book. So we can look up, here's that hydrogen-carbon bond. Bond energy is 414 kilojoules per mole. That's per mole of those bonds. One thing I'd like to point out to you is that a carbon-oxygen double bond, the average is 736, but there's an asterisk here. So then we should look for what the asterisk means, and that's down there in the bottom. It's 799 in carbon dioxide. That's a significant difference, and carbon monoxide is a very common compound, so that little exception is listed. The rest of them are all just regular averages. If you look at nitrogen, single, double, triple bond, we see that the bond energy increases substantially, which should make sense. Any questions? So how can we use bond energies to estimate enthalpy changes? When bonds are broken, that's an endothermic process. We have to put energy into the molecule. When bonds are formed, energy is released. So that's an exothermic process. So we can estimate the change in energy for a reaction by comparing all the bonds that were broken and all the bonds that were formed. So we can take the sum of all the bonds that are broken. That's going to be a positive number because it always requires energy to break a bond. And we can add the sum of all the bonds formed. Those will be negative because energy is released. Does that make sense? Here we have a diagram. Enthalpy increasing as we go up. It's a type of energy. So here we've got methane and chlorine, and we're looking at them reacting to form chloromethane and hydrogen chloride. So we can think of what's happening here as, well, we have to break this chlorine-chlorine bond, and we have to break one of the carbon-hydrogen bonds in order for this reaction to occur. So we can figure out how much energy is required putting in to break those bonds. And then when new bonds are formed, we're making a chlorine-carbon bond and a hydrogen-chlorine bond. When those bonds are made, energy is released. In this case, more energy is released than was needed to break the bonds, and so overall the reaction's exothermic. When two chemicals react and release energy into the surroundings, that energy has to come from somewhere, right? It's not created. It's just transferred. It's changed. So the energy in chemicals is stored in their bonds. If the reaction forms substances with weaker bonds, that difference in energy is released as heat into the environment. Any questions? We often say that energy is stored in chemical bonds. I think I just said that, right? Breaking the bond requires energy. It's the forming of bonds that releases energy. So an energy-rich compound, something like octane, which is what's in gasoline. You burn it in the car engine and it produces a lot of energy. An energy-rich compound undergoes reactions in which weak bonds are broken and strong bonds are formed. And that releases the energy that was stored in the chemical bonds. So let's do an example. A potential future fuel is methanol. And they've already started... No, never mind. That was ethanol. Write a balanced equation for the combustion of gaseous methanol and use bond energies to calculate the enthalpy of combustion of methanol in kilojoules per mole. So the first thing is write a balanced equation. Well, so we've got methanol combusting. What's the other reactant then? Oxygen. Got to have oxygen for things to burn. And what products will be formed? CO2. Water and CO2. Because those are the two compounds that form when a compound containing carbon, hydrogen, and oxygen is burned. So here we have the methanol. It's just carbon, hydrogen, and oxygen. Combustion says it's reacting with oxygen. Products will be CO2 and H2O always. And we have to balance the reaction. So we've got one carbon on this side and one carbon on that side. And then hydrogens, we've got 3 plus 1, 4. And over here we only have 2. So let's put a 2 in front of H2O. So now we've got our hydrogens balanced. And then here we've got 2 oxygens and 2 oxygens. We have a total of 4 oxygens over here. And 2 plus 1 is 3 oxygens. So we could put a 2 in front of carbon, but then that's going to mess up the hydrogens and the carbons, right? So instead of doing that, we could use a fraction, or we could say, well, we've got an odd-even problem, let's just double things. I'm going to do the fraction one this time. So what I want from this is 3 oxygens, right? But they're coming in pairs. So I need 1.5 pairs of oxygen. 1.5 is 3 halves. Right? So this is balanced, but how can we have 1.5 oxygen molecules? Right? We can't. So we're going to multiply everything by 2 to clear that fraction. So 2 of these, multiplying this by 2 gives us 3. And we're going to change this 2 into a 4. And then this is going to have a 2 in front of it. So then we have to double check because it's easy to screw up here. 2 carbons, 2 carbons. 3 plus 1 is 4 times 2, 8 hydrogens. 4 times 2, 8 hydrogens. And over here we've got 6 oxygens here plus 2, 8. 8 oxygens total. And over here we have 4 oxygens and 4, 8. Got to have a balanced chemical equation. So we're supposed to use bond energies to calculate the enthalpy of combustion. Now in the diagram, well, let's just go back there. When we looked at this diagram, we just looked at breaking the bonds that were necessary. And you can certainly do that. You can look at this and say, well, I just need to break one of these carbon-hydrogen bonds. But when we've got something like this, it's difficult to look at that, especially for a beginning student, and identify what bonds are going to be broken and what are going to stay, right? So the other method, which is kind of it's like a shotgun method, just like shoot everything, right? Instead of targeting something. It's probably not a good analogy. We're just going to say, well, let's just break all the bonds and make all the new ones. And that way we don't have to figure out what's staying and what's going. We need to see the Lewis structures to do this because we have to identify, are these carbon bonds, hydrogen bonds, oxygen bonds? Are they double, single? How are they all put together? So let's look at this. Methanol, you have to draw the Lewis structure. You're going to end up with this. The way this formula is written implies that this hydrogen is on the oxygen and that these 3 hydrogens are on the carbon. And so it kind of gives us a guideline or a direction for making that. Now there'd be 2 lone pairs on the oxygen. We don't actually have to draw those in. So we've got 2 of these, and then we've got O2. Well, let's just go ahead and do the lone pairs. Let's make this a little smaller. Maybe a little smaller than that. For oxygen, oxygen has a double bond, and then each of these is going to have 2 lone pairs. And then over here we're forming H2O. And CO2. With the Lewis structures, we can see what kind of bonds we have. So what we're going to do is we're going to look at this methanol molecule, and we're going to say, well, let's just break all the bonds. Basically, it's, you're building with Legos, and you have these 2 Lego structures, and you need to change them up and make something new. And instead of figuring out, well, how do I take this one just a little bit apart and put it back together, I'm just going to break it into single blocks, right? Take all the blocks apart, and then I'm going to start fresh over here. So we're going to look at this molecule and identify what kind of bonds are there in that molecule. So there are carbon-hydrogen bonds, right? So we've got carbon-hydrogen, we've got carbon-oxygen, and what's the other one? Oxygen-hydrogen. How many carbon-hydrogen bonds are there? 3. So there's 3 of those. There's 1 carbon-oxygen and 1 oxygen-hydrogen. In the O2, we have a oxygen double bond. There's just the 1, right? Let's also think, how many molecules of methanol are we taking apart? 2 of them. So then we don't have just 3 carbon-hydrogen bonds. We've got 6. And we've got 2 of these and 2 of those. And for the oxygen, we're taking apart 3 molecules, so it's 3 oxygen-oxygen double bonds being broken. That make sense? Then let's go over here and see what we're making. So for water, we're making oxygen-hydrogen bond. We're making 2 of those for every water, and a carbon-oxygen double bond for the CO2, and there's 2 of those, 2 of these bonds in this one molecule. We've got 4 water molecules, though, that we're taking apart. So we actually have 8 oxygen-hydrogen bonds, and we're making 2 carbon dioxides, so we're actually making 4 of those bonds. You okay with this? Now we need to go and look up the bond energies. So I'm going to write these on the board because my short-term memory is shot. So we needed an oxygen-oxygen double bond. That's 498. That's right there. We've got a carbon-oxygen double bond. Carbon-oxygen double bond. Is our carbon-oxygen double bond in CO2? Yes, it is. So then we're using the 799 instead of the other one. We had oxygen-hydrogen bonds. Let's see, where did those go? Hydrogen-oxygen, 464. We had hydrogen-carbon, 414. And I think we had a carbon-oxygen single bond, which would be right here, 360. Did I miss any? Okay, so let's go back here. I think I got them, yeah. Okay. So we're breaking 6 moles of carbon-hydrogen bonds. So that's 6 times the bond energy for the carbon-hydrogen bond, 414. And those units are kilojoules. We're going to break 2 moles of carbon-oxygen single bonds. So that's 2 times 360. And we're breaking 2 moles of oxygen-hydrogen bonds, 464. And 3 moles of oxygen-oxygen double bonds, 498. So we can add all of these up. So we've got 6 times 414 plus 2 times 360 plus 2 times 464 plus 3 times 498. It's a little bit like going to the store and shopping. I've got 2 of these and they each cost this much, and we're just adding them all up together. So this is our total cost, $56.26. You could think of this as going to the consignment store, and you're going to buy some stuff and you're going to sell some stuff. And this is the stuff you're buying. This is what you have to pay for. You're giving them money, right? Over here, this is what you're selling. This is what's giving money back to you. So over here, we've got 2 oxygen-hydrogen bonds, 464, and 4 carbon-oxygen double bonds in CO2, so those are $7.99 each. 2 times 464 plus 4 times $7.99. Total over here is 4124. Yes, it's 8. Thank you. So this is an 8. That's going to change things up a bit. Let's try that again. How about 6908? Does that sound better? Thank you. 6908. These bonds are being formed. That releases energy. So these are all negative. They're releasing energy. So I'm just going to put negative signs here. So this is releasing 6908 kilojoules of energy. And this was requiring 5626. So you go to the consignment store and you're selling some jeans and t-shirts, and then you're buying a dress and a handbag and 3 pairs of shoes or something, right? So you're spending this much, but you're selling this much. You add those two together, and that tells you whether you owe the store or they owe you, right? So we've got the negative 6908 plus the 5626. So we're going to add those two together, and we get negative 1282. Yes, we have to divide by 2. This is the amount of energy to do this reaction as written. That's 2 moles of methanol, right? We want to know how much energy is released per mole of methanol. So this is the amount of energy for this reaction. To find the moles per methanol, we're going to take that amount of energy, minus 1282 kilojoules. That was for 2 moles of ethanol. And so we divide by 2. And we get negative 641 kilojoules per mole. Any questions? Is that reaction endothermic or exothermic? Exothermic. It's releasing energy. That's why methanol is a potential fuel, because when it burns, it releases energy. Bond lengths. We've talked about the, well, never mind. Bond lengths. The average length of a bond between 2 particular atoms in a large number of compounds. So again, the bond lengths are going to vary a little bit in different molecules. We don't care necessarily about those small variations, so we're going to look at overall averages. So we'll observe that double bonds are shorter than single bonds, and triple bonds are shorter than double bonds. So here we've got carbon bonded with carbon, a triple, a double, and a single bond. The bond length is 120 picometers for the triple bond, 134 for the double bond, and 154 for the single bond. The single bond, the atoms are further apart from each other. Double bond pulls them together closer, and a triple bond pulls them together even closer. And we see a related trend in bond strength. The shorter bond is the strongest bond, and the longest bond is the weakest bond. There are, of course, exceptions, but it's a general trend. We can look up bond lengths in a table as well. There they are.